Hello, everyone. My name is Mohali from Toshiba Europe Limited, Cambridge Research Laboratory. The paper I'm presenting here is towards a unified end-to-end language understanding system for speech and text inputs. This presentation will be given in 4 parts. And so firstly, we're going to look at the base of the proposed system, which is an end-to-end spoken language understanding system based on the MARC-CDC approach. And secondly, we will focus on the proposed unified language understanding system for speech and text inputs, which we call ASRU system. This is followed by the experimental results and finally the conclusions. So firstly, so our proposed system is an extension to a previously proposed non-autoregressive MARC-CDC SU system. So this system is composed of an encoder and a decoder. So firstly, the speech signal will go into the encoder to produce the vocabulary distribution for all the frames. And based on the CDC decoding scheme, we will work out the raw CDC outputs. And we mask out the tokens in the CDC outputs that have low confidence score or low probability because they are not reliable, need to be refined. And also at the same time, we add a special token COS in front of the CDC output sequence to perform decoding. And the hidden state of this COS token would be used to recognize the intent of the actions. And the rest of the hidden states would be used to recognize the slot labels as well as the refined ASR outputs. So this framework is able to perform ASR and SAU tasks at the same time jointly. So extended from this framework, we aim to integrate the NLU functionalities to it. So we can notice that from the architecture, the use of the encoder state X, which comes from the speech, the use of this element in the decoder prevents the system from performing NLU tasks that uses plain text inputs. So a simple solution is to feed the text sequence into the decoder directly. So in this case, we don't touch the encoder at all. Well, at the encoder side, we also bypass the cross-tension module of all the decoder layers, so that this would avoid the use of X, as we could see in figure B. And simultaneously, the self-tension module and the feed-forward network at each decoder layer are kept active, and they are shared with the ASR and SAU tasks, so that we don't have any redundant parameters. Everything is shared among all of the tasks. And during training, the loss function of the NLU tasks is interpolated to that of the ASR and SAU tasks through multitask learning. So by the end, this framework will be able to handle ASR, SAU, and NLU tasks altogether in a unified architecture. We also explored the initialization with pre-trained off-the-shelf speech and text models. So we firstly initialized the speech encoder with WaveLM base model. And on top of it, we also put an upper layer to perform the CDC decoding for both training and inference. And then the decoder is also initialized with the off-the-shelf model as BERT-based model. Because the BERT model doesn't have the cross-tension module that is useful for ASR and SAU tasks. So we randomly initialize the cross-tension module and insert it into each layer of the BERT model. So that the model will be able to handle all of those tasks. So in this case, a two-stage training was carried out. So firstly, we will train the BERT parameters in the decoder on the NLU task. And at a later stage, we will freeze these parameters and fine-tune the decoder parameters for ASR and SAU with the cross-tension parameters. Because otherwise, we believe if we don't freeze the parameters, then the NLU performance will be degraded quite a lot. And we carried out experiments on the SLAB dataset, and in this table we report the weather rate for ASR and intent classification accuracy, slot fitting SAU F1 score, and slot fitting NLU F1 score on the test set of the SLAB dataset. We also provide the number of parameters of each system. So we could see that from this table, the proposed SNLU system achieved very comparable performance to both the end-to-end SAU system and the separate NLU system, but with much less number of parameters. And also by injecting the wave LM and BERT model into the system, we could see that so on all of the metrics, the performance has been very largely improved. So conclusions. So in this work, we propose a unified architecture called SNLU that could flexibly handle both speech and text input up to the user's need. And the proposed system achieves the performance that is comparable to the separate end-to-end SAU and NLU modules, but with relatively 43.7% less number of parameters. And we also explored the incorporation of the pre-trained speech and language models into the framework, which brings noticeable performance gains to the proposed SNLU system. Okay, so this is the end of the presentation, and thank you for your attention. If you have any questions, please contact me using this email address. Thank you.